Let's take a closer look at Planck's equation for blackbody radiation and see how it agrees with experiment. What happens at very high frequencies? We can see that the intensity depends on two factors. The first factor, h pi nu squared over c cubed, depends on the square of the frequency nu. As nu goes to infinity, we expect this factor to go to infinity as well. What about the second factor? Since x is h nu over kb times t, x goes to infinity as nu goes to infinity. This makes e to the power x minus 1, which is in the denominator of the second factor, to go to infinity as well. A very large denominator in the second factor makes the second factor go to 0 as nu goes to infinity. Because the second factor is an exponential decay, while the first factor only goes up quadratically, the second factor wins as nu approaches infinity. In other words, the entire right-hand side of the equation goes to 0 as nu approaches infinity. Therefore, the intensity goes to 0 as nu approaches infinity, which agrees with experiment. What about at very low frequencies? We can see that as nu approaches 0, x approaches 0 as well. From calculus, we know that e to the power x can be written as 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. As x approaches 0, e to the power x approaches 1 plus x. Substituting 1 plus x for e to the power x, we see that e to the x minus 1 approaches x. Substituting x for e to the x minus 1, then substituting h nu over kb times t for x, gives us the Rayleigh-Jeans law, which, as we have previously seen, agrees well with experiment at very low frequencies. To derive Wien's law from Planck's radiation formula, all we have to do is take the derivative of the spectral energy density per unit wavelength with respect to wavelength. The derivative is equal to 0 when lambda equals lambda max. Setting the derivative equal to 0 allows us to solve for lambda max. Before that, however, we need to derive the expression for the spectral energy density function per unit wavelength. You cannot simply replace nu in the spectral density function per unit frequency with c over lambda. You need to apply the chain rule by multiplying it with the derivative of nu with respect to lambda, then switch algebraic signs since nu and lambda are inversely proportional. The spectral energy density per unit wavelength can then be shown to be equal to 8 pi hc over lambda to the fifth power times 1 over e to the x minus 1. Taking the derivative of rho with respect to lambda, setting the derivative equal to 0, and solving for lambda gives us the Wien's displacement law. Lambda max is equal to a constant divided by t, with the constant being h times c over 4.965 times the Boltzmann's constant.